Hello, my name is James Kress, and this is a research presentation for ISC 2020. My talk is entitled Opportunities for Cost Savings with In-Transit Visualization. I'm going to start off today with some motivation. So in 2015 at ISAB, we had a position paper on in-situ comparison factors. And so that paper, we had 10 different factors that we posited for comparing inline versus in-transit in situ. And we posited that there were 3 different factors that more favored inline, and there were 4 different factors that more favored in transit, and 3 that ended up being ties. But during that presentation, we were met with some skepticism from the audience on what we had chosen as our winners. And the one that was met with the most skepticism was scalability. And so that's really where we decided to start focusing some of our research and to address the issues that people were having with our chosen winner in this paper. And so thinking more about it, we started thinking that, well, even if in-transit is more scalable, that doesn't necessarily mean that it's better to use from potentially a cost perspective. And so we decided that maybe scalability should actually be a question of cost. Is inline or in-transit more cost-effective to use? Because even if something's more scalable, that doesn't necessarily mean that it's going to cost less to use in the end. So that's the focus of today's paper, is really this cost question. And so what do I mean by cost? So in this paper, we're measuring cost in terms of node seconds. So we have our number of nodes multiplied by the number of seconds in use. So for example, let's say we have 10 nodes running for 20 seconds. This is a 200 node second allocation. And so now here's 2 examples. We have an inline allocation on the left and an in-transit allocation on the right. And these are progressing over time. So for the inline allocation, let's say we're running on 10,000 nodes, and all of these steps take 21 seconds. On the in-transit side, we still have the same 10,000 nodes for the simulation, but we have to dedicate another 1,000 nodes to do the visualization, and this in total takes 17 seconds. So our inline total cost then is 210,000 node seconds, and our in-transit total cost is 187,000 node seconds. And so now this is a general idea of cost in terms of in-transit and inline. In situ, but I'd like to get into some different scenarios to give you a better intuition about how you can start to predict and think about what the cost might be of a given run. So for example, let's say that we have an inline visualization scenario here, where we have a simulation cycle time of 15 seconds and a visualization time of 1 second. And so this is all running on 15 nodes. So the simulation starts up, it runs for 15 seconds, it pauses, the visualization starts, runs for 1 second, hands control back to the simulation, and it runs again, followed by the visualization again. And so this then is what it looks like in inline. What does that look like in transit? So for in transit, what happens if we dedicate just 1 additional node to this problem? So in total now we have 16 nodes. So we still have the same 15 nodes doing the simulation, but we have 1 node doing the visualization. So here, the simulation cycle time is still 15 seconds. And if everything scaled exactly perfectly from the inline example, it should take 15 seconds to do the visualization all on a single node. So that's a hypothetical in this scenario. But if that were the case, what would our total cost look like? So for inline, we have 15 nodes, each running for 16 seconds per node, for a total of 240 node seconds. On the in-transit side on the right, we have 16 nodes, each running for 15 seconds per node, which is still 240 node seconds. So these are the same, but like I said, this was an ideal balance. So what else could happen? So we have the same inline visualization scenario again, 15 seconds simulation cycle time. But what happens if our visualization time is doubled? So in this case, the simulation runs for 15 seconds, pauses, the visualization runs for 2 seconds. In transit, what does that mean? So that means for in transit, we have the simulation cycle time of 15 seconds, but now the visualization time is going to take 30 seconds all on 1 node. So the simulation runs for 15 seconds, and then for the other 15 seconds, they all sit idle while the visualization completes all on 1 node. And so what does this mean? This means that we have 15 seconds to do 30 seconds worth of work. So this is bad. And so what are some options we could have in this case? Well, first, like we just saw, we could block the simulation from advancing. And that's what we did in this example. The second is we could get more resources, don't do all of the work on one node. Or the third option is we could skip visualizing the next time slice so that we could just let the simulation proceed and skip that time step in terms of visualization. And so all of these are reasonable choices, but with this work and all of our results, we chose option 1, so we blocked. And so what does cost look like now that we have a longer visualization time? So our cost inline is 15 nodes, each for 17 seconds per node, for a total of 255 node seconds. In transit, we have 16 nodes for 30 seconds per node, for a total of 480 node seconds. So now, the cost in terms of node seconds is a lot faster for inline. But what else could happen? So there's one missing consideration that we have here, and that's data transfer. So it takes time to transfer data from the simulation nodes to the visualization nodes. And so this is an additional cost that we have to be aware of. So let's go back to an in-transit example. So now we have a simulation cycle time of 15 seconds. It takes maybe 1 second to transfer our data to the visualization node, and then 15 seconds again to do the visualization. So what we have is we have the simulation running on 15 nodes. The simulation pauses, data transfer starts on 15 nodes, and then that all gets sent down to our 16th node. That completes, the visualization starts, and the simulation starts the next time step. And then all of that pauses, the data transfer happens, and it starts again. So what does our cost look like now when we include transfer time? So for inline, we have 15 nodes for 16 seconds per node for a total of 240 node seconds. In transit, however, it's now 16 nodes, each for 16 seconds per node for a total of 256 node seconds. So as before, these two examples were equal. However, now the transfer time caused in transit to be slower. And so that highlights some of the pitfalls for in-transit visualization. Our in-transit resources are idle, that's going to cause our cost to go up. If we don't have enough work for in-transit resources, or maybe we have just too many resources allocated. Another pitfall is that maybe in-transit cannot keep up. Do we block? Do we skip data? Do we get more resources? All of those are really open questions. And then the third pitfall is our transfer times. But this research is about how in-transit processing can lead to a cost savings. But so far, we've only identified problems. So how can in-transit help? So as a slide repeat, this is our inline visualization scenario, 15-second cycle time and a 2-second visualization time. So the sim runs, followed by the visualization, and that goes on and on. On the in-transit side, we were positing that this would take 30 seconds if everything scaled exactly perfectly. However, the big idea here is that with inline running at scale, inline is running at scale, whereas in transit is transferring all of the data to a single node. So parallel coordination at scale creates inefficiencies. And with in transit running at a lower concurrency, this reduces our inefficiency. So the dream scenario then is that this 30 node seconds of work on 15 nodes actually is 15 node seconds of work on a single node. And this actually happens. This is an important finding from this research, that we do see this scaling happening. So let's talk a little bit now about scalability. What does that mean in general? So transferring data once to a separate allocation has the potential to reduce overall data movement in communication-heavy visualization workflows and increase node utilization. So what does that mean pictorially? So this is a little more interesting example. So let's say we have in-transit on the left and inline on the right. And so what we're saying here is that scalability at, say, 1,000,000 cores for in-transit can be thought of the Indy 500. So where everything is running really fast, there's only a few cars running, nothing is being slowed down. Whereas on the inline side, we can think of this scalability at 1 billion cores and more like the LA freeway gridlock, where there's so many different cars running, so much communication, that everything just gets bogged down. So that then is really the central study question in this work is cost. Which in-situ paradigm is the most efficient and under what circumstances? And then parenthetically, does in-transit's increased scalability ever pay for itself? Our hypothesis with this work is that in-transit will cost less than inline in certain configurations. And the main finding we have in this paper is something we termed VCEF, or the Visualization Cost Efficiency Factor. And this is a measure of how much more efficiently an algorithm runs on a smaller resource. The way this is calculated is we have our inline visualization time multiplied by our number of nodes, divided by our in-transit visualization time multiplied by our number of nodes used for in-transit visualization. So for example, let's say our inline visualization time is 1 second, and we're running on 1,000 nodes. And our in-transit visualization time is 50 seconds, and we're running on 10 nodes. So this becomes 1,000 divided by 500, or 2. And so what that means then is that inline costs 2 times that of in-transit. So in-transit is 2 times more efficient than inline in that case. And then the other hypothesis we have is that VCEF, in some cases, is actually going to offset our transfer, idle, and blocking costs. The way we considered this is from the perspective of a cost model. And due to time today, we're just going to omit to the discussion of cost model in this presentation, and we're going to get into some of the results that are a little bit more interesting. So all of our cost model captures the concepts from our previous slides, and I encourage you to please see the paper for the details of that cost model. So I'd like to now do our experimental overview. So we used 3 primary technologies in this work. We used Ascent, which is a flyweight in situ infrastructure that supports both distributed memory and shared memory parallelism. We used VTKM, which is a scientific visualization toolkit for emerging processor architectures. And we used Audios, which is an I/O middleware library that exposes inline and in-transit paradigms. And we accomplished in-transit with Audios via an RDMA memory-to-memory transport mechanism. We had 2 visualization tasks we performed in our study. We had a computation-bound task and a communication-bound task. Our computation-bound task was isocontouring plus parallel rendering. So isocontouring happened in 2 primary steps. First, the energy variable, which is the variable we were interested in, had to be recentered. And then we performed an isocontour at 2 levels, at 33% and then 67% between the minimum and maximum values. Next, we did a parallel rendering. This again occurred in 2 steps. First, each process locally rendered its data, and then second, a hierarchical reduction was performed to composite the final image. Our communication-bound algorithm was volume rendering. It occurred in 2 steps also. First, each process locally rendered the energy variable, and then second, a direct send was performed to composite the final image. And an overview, summary of our experiment is we had 255 individual runs. Our simulation was a hydrodynamic simulation with varied cycle times. We had 3 different cycle times with that simulation. We had one that was approximately 5 seconds, one of 15 seconds, and one of 25 seconds. We had 9 different concurrency settings. We ran up to 32,768 cores and up to 68 billion total cells in the simulation. For processing, we had 2 different paradigms. First, we had our inline processing paradigm. And next, we had an in-transit processing paradigm. And so our in-transit occurred at 3 different options as well. We had a 12%, 25%, and 50% of simulation resources. And so what that means is that if the simulation was running on 100 nodes, in-transit was allocated an additional 12%, 25%, or 50% of those nodes. So in the case of 100 nodes, 12%, we had a total allocation of 112 nodes. We had 2 different configurations. First, we had an inline configuration where we had 16 MPI ranks per node. And second, we had an in-transit configuration where we had 4 MPI ranks per node plus 4 open MP threads per rank. And so I do want to point out here that our experimental setup did affect our VCEF values in 2 primary ways. First, we had higher VCEF values due to using fewer nodes, because we're using 12, 25%, or 50% of SIM resources. And we had a higher VCEF value due to using fewer ranks per node. So I'll talk about that in our VCEF results slide, where we actually quantified the effect of having fewer ranks per node. And if you want to see any more details about our experimental setup, please see the paper for more details. All right, so next I'd like to jump into some results. So the first most interesting result is our VCEF magnitude chart. And so if you remember, VCEF is the measure of how much more efficiently in-transit runs versus inline. And for your reference, the VCEF equation that we have is here in the left-hand side of this slide. And so I'd like to take a second now to explain this graph. It's a little bit complicated, but in general, the x-axis is our inline visualization cycle time. The y-axis is our visualization cost efficiency factor. And on the y-axis, higher values are better, which means that it's more efficient. We have 2 different symbols on this chart. We have triangles, which is our isosurfacing results, and circles, which are our volume rendering results. And we have all of our different test cases here for ALEC 12 to ALEC 50% with each of our 3 different simulation cycle times. And then the graph progresses from small symbols to large symbols in terms of the concurrency that we ran. So looking at this chart now, we can see just right away that many of our VCEF values are high. Most of them are between 1 and 9. With only a couple that drop below 1 at the bottom of the chart. And so what that means, if it drops below 1, it means that the in-transit was actually less cost efficient than the inline. So in almost every case, in-transit was more cost efficient. And if you remember a few seconds ago, I mentioned that our higher VCEF values were due to 2 factors, running on fewer nodes and running on fewer ranks per node. So when we did a quantification, what we found was that our VCEF values would essentially be half of what we're presenting in this slide if we had run at a full 16 ranks per node in transit. So just as a point of reference. And looking further, we can see that there's a clear distinction between our different workflows. We have the volume rendering workload, which is very well centered in the upper part of the graph, and the isosurfacing workflow, which is tightly clustered at the bottom of the graph. And so we can see with those 2 that we have significant room for cost-efficient use of in-transit. So for volume rendering, what we can see is that until we got up to about 16,384 cores, volume rendering wasn't scaling or wasn't being much more cost-efficient versus the inline. But once we got up to higher core counts, we started seeing 4, 5, and 6x improvements over inline. For isosurfacing, we're starting off right away being a lot more cost efficient, and then it jumps clear up to 9x in some cases. Next, I'd like to look at a feasibility of cost savings. So just because our VCEF values were high, that doesn't necessarily mean that we were more cost effective. It just means that we had a potential to be more cost effective. So with this chart, this looks at which of our test cases could have achieved a cost savings. So in the center here, a black line is our equality line. Above that line, in-transit can potentially cost less. Below, inline, definitely costs less. So some of the observations we can make on this chart is that some of our configurations are clearly bad from the start. A lot of our isosurfacing results start off below the line. Some of them start off below the line and stay below the line for their entire lifetimes. Or on the other hand, our volume rendering results do very well. A lot of them start below the line, but then they start to jump above the line fairly quickly. One other thing to point out in this chart is that the filled glyphs are actually where we saw a cost savings in the end, and the empty glyphs are where the cost savings were not achieved. So the reason that there are some unfilled glyphs above the line is that our VCEF value wasn't high enough to allow us to achieve the cost savings. It had the potential, but we didn't achieve it. And so we can see in this chart, there's a really high percentage of feasible cases of cost savings. And so overall, 30 of 58 possible cases did achieve a cost savings in our study, for a total of 20% of intrinsic cases where we saved on cost. And finally, as our concurrency increases, our inline costs rise faster than our transfer costs. And so what does that mean? So on the x-axis, that's our proportional transfer and resource cost versus the y-axis, which is our proportional inline biz cost. And so what we want to see is that for in transit, the transfer cost needs to be less than the inline visualization cost. And then the last result I'd like to talk about today is our achieved VCEF values versus our required VCEF values. And so what does that mean? And so what this means is that what VCEF value did we achieve versus what value did we need in order to not block the simulation. So it's possible to block the simulation in transit and still achieve a cost savings, but in an ideal world, we would not block the simulation. And so this chart looks at what values we got versus what we needed to not block the simulation. And so this plot uses only cases where our cost savings was achieved. That's why there are fewer points here. So some observations we can make is that we did have a cost savings possible with blocking. So if you look at the volume rendering result, clear over on the right in the red, we can see that we achieved around a 9.5x VCEF value in that test case. However, in order to not block the simulation, we needed a 25x VCEF value. So that was a huge difference between what we got versus what we needed, but because it was so much less efficient in line, in transit was still able to be more cost efficient. Next, we see that VCEF prevented blocking in about 2/3 of our cases, which is quite high. Next, volume rendering achieved the most. So you can see most of the points here are volume rendering points. And then our isosurfacing started to achieve at high concurrency. So most of these isosurfacing results are up at our 16,384 process count cases. All right, so finally, let's move on to the conclusion. So in conclusion, we identified VCEF and we have demonstrated VCEF values. We have found that our values were surprisingly high, and we can use VCEF to predict in situ cost efficiency. We also found that configuration exists where one paradigm outperforms the other. And this is somewhat surprising for in transit, meaning that it can not only be faster than inline, but also more cost effective. And in transit cost efficiency is impossible in some cases. We can't achieve it. Finally, total cost. So in terms of total cost, if that's what we're concerned about, inline is generally more cost effective for computation-heavy algorithms at low concurrency, whereas in transit is generally more cost effective with communication-heavy workloads and computation-heavy algorithms at large scale. And finally, we provide models to quantify the cost of in situ visualization and provide insights for setting up future in situ visualization workflows. And so we'd like to conclude now with thanking the sponsors for ISC. Thank you.